Section 4.4 talks about linear independence. Suppose S consists of these vectors. So it's a set of two or more vectors. And that is in the vector space V. So we know it's closed under addition and constant multiplication, and check if zero is in there. Then S is said to be a linearly independent set if no vectors in S, none of those vectors, can be expressed as a linear combination of the others. That means you can't take few of those vectors, multiply them, and get another vector in there. That means those vectors cannot be found by any linear combination of the set. If no vector of S can be expressed as a linear combination of the other. A set that is not linearly dependent is called linearly dependent. So linearly independent, linearly dependent. If S has only one vector, just one, we will agree that it is linearly independent because there's nothing you could multiply it with to set it equal to another to figure that out. You must have at least two, right? And only if the vector is non-zero. All right. A non-empty set, say that's the one, in a vector space V is linearly independent if and only if, that's a massive deal, the only coefficient satisfying. So if you take all of these vectors, multiply them by weights like we did in the previous section, set them equal to zero, then the only way that will work if and only if the coefficients are all zero. Every single one is zero, no exception. So linearly dependent when you have V1 and V2 matching on a line or in opposite direction, they're still in the same line. But if they are not multiple of each other, that means those two vectors are linearly independent. That's 2 dimensions. If you go for 3 dimensions, those 3 vectors are linearly dependent because they are on this plane. Here, those 2 vectors line up the same way, and this is still on the same plane. Here, we're assuming there's an angle between those. Those 2 are the vectors in V, and those are 2 on the plane, but this one is not. So let's set V1, V2, all Vm be a set of vectors in Rn. Then if this is bigger than this, it's automatically linearly dependent. If you have more equations than unknowns, then one of the equations has to go out. Meaning if you have 2 by 2, x and y, right, you only need 2 equations. If you get 3 equations, that means the third equation must be multiple of the other 2. So you can't have more vectors than the dimensions. 2 dimensions, you get 2 by 2. 3 dimensions, 3 by 3, 4 by 4, and so on and so forth. The Wronskian is another way of figuring out whether you have linearly independent or dependent, provided you're given functions. It's a lot of work to do that with functions. This is a quick way of checking. And if these functions are 1 less n differentiable, that means the derivative exists, then this is what you do. You list f1, you list f2, you list f3, all the way to f sub n. And what you do, you take a derivative that many times, make sure this is matching, the derivatives are matching how many of those unknowns you have. And you take the determinant of that. If the determinant doesn't equal 0, then they are linearly independent. And if the determinant equals 0, then they are linearly dependent. So you list the functions, take a derivative of each until you get to n minus 1, right? And that will match. And then take the determinant of this. And if the determinant equals 0, it's linearly dependent. I suggest you memorize one of those. This is called the Wronskian, the determinant of f list, the list of f functions and taking derivatives. That's what it's called. So we have this method we have this method. We could take k times v1 plus k times v2, k times v3, set equal to 0, and see if the only solution is zeros, it's fine. If it's anything other than that, it's linearly dependent. Here's the first example. In each part, determine whether the factors are linearly independent. These are vectors. So if I am to take k1 times v1 plus k2 times, and I'm going to write the first problem out just for you to see it again, plus k3 times 1, 1, 3, set it equal to the 0 vector, 0, 0, 0. Then this is really negative 3k1 plus 5k2 plus k3. This is 0 minus, I'm just writing 0 for your notes. And this is 4k1. This is 2k2. And this is 3k3, actually. I meant this. Equal to 0. Well, the only way that could happen if I have the first equation equals 0 and the second equation. Now, of course, you really don't have to show me all of these steps. I'm hoping you're going to jump from this to this straight. From this, you're going to skip all of this mess. And you're going to jump straight and say, look, the augmented matrix is negative 3, 5, 1. So the K1 would look like that. Negative 1, 2, and 1, 1, 3. Set them equals 0, 0, 0, and solve. And if I am to work this out, if I reduce this, and you know how that works, I'm looking at 1, 0, 0, 0, 0, 1, 0, 0, and 0, 0, 1, 0. That indicates that k1 equal k2 equal k3, which is 0. Therefore, it's linearly independent. So if the only solution would be all zeros, that will indicate that those vectors are linearly independent. And if there's a solution other than that, then we say those are linearly independent. Here's another problem. Then there's no need for me to write this problem out, but I'm going to do it anyways. If I take this times k1, and I'll say why again. This class is not about crunching numbers. We've been doing that for a while until you really grasp what we're doing with all of those. But the idea is for you just to start applying what you know. Looking at this, I know these are linearly dependent, and I'll point that out once I get to the problems. That's negative 0, 1, 3, 2, 5, 6, negative 1, 1, and 7, 0, negative 2, equaling 0, equaling 0, equaling 0. Do you notice this is K1, this is K2, this is K3, this is K4? And do you notice we only have 3 vectors? We have 4 vectors. So we have one more vector than we need. We really have x, if you simplify this, reduce this, so the augmented matrix really reduces to 1, 0, 0, 1, 0, 0, 1, 0, negative 1, 0, 0, 0, 1, 1, 0. And obviously, we have the 0. Since this could be anything at once, so it could be 1, it could be 3, right? And that's not identically 0. This is linearly dependent. Again, I have more vectors than the unknowns. Obviously, I have one extra vector I have to really get rid of, and that by itself is gonna make it linearly dependent. If I look at this problem, in each part determine whether the vectors are linearly independent or are they linearly dependent of P2. Well, for P2, we know how that works. Let's take A multiplied by 2 negative x plus 4x squared plus B times 3 plus 6x. Of course, you could use k sub 1, k sub 2, k sub 3. And if I take this and set it equal to 0, 0, 0, or just simply the 0 vector, well, guess how this works. When I multiply this, I'm going to get with the constant coefficient, which is 2a plus 3b plus 2c, plus a negative a plus 6b plus 10c times x, plus that was a 4x squared plus if I want the x squared, that's 4a plus 2b and minus 4c, and all of that equal the 0 vector. Well, guess what? It turns out I'm solving this matrix. The a, the b, the c, and of course you really don't have to put those in there. And if I reduce this, I end up with 1, 0, 0, 0, 0, 1, 0, 0, and 0, 0, 1, 0. So obviously C is 3, C is 0. Oh my god, I'm really tired. And A is 0. Therefore, linearly independent. So that's how it works. The next problem, I'm looking at this and I'm gonna take a sub 1 times, so that goes, if I put a in there, that's 1, 3, 3, b in there, that'll be 0, 3, 4, and c in there, that'll be c in there, that'll be 5, 6, 7. I noticed I put a 3 there. That's actually a 1 there. Then we have 5, 6, oh, what is 7? It's 5, 6, 3. And for the last, we got the 7, the 2, and the negative 1. Set that equal to 0, 0, 0, and solve, right? A, B, C, and let's say D. I forgot about that. And if I row reduce this, I'm getting 1, 0, 0, negative 17 over 4, 0, 0, 1, 0, 3 fourth, 0, 0, 0, 1, 9 fourth, and a 0. And of course, we could have d equal t. Well, again, automatically, by d being t not 0, not identically 0, this is linearly dependent. Now, I could have figured that out just by looking at, but you want to make sure that those are more than, those are 4 equations and 3 unknowns, because we know 3 unknowns because it's ax squared plus bx plus c equals 0. There are only 3 unknowns in any quadratic, and those happen to have 4 vectors. Well, here, if I multiply this by, I was going to write K1, but there's a K, A, B, C, right? And set it equal to 0, 0, 0, 0. So from last class meeting, that's A1. That is 1, 0, 1, K. And that is negative 1, 0, K1. And that is 2, 0, 1, 3. And I'm gonna set those equal to 0, 0, 0 and solve. It seems I messed up. This is 1, 0, 1k. This is negative 1, 0, k1. That's right. And this is 2, 0, 1, 3. Okay, well, this is all zeros. Basically, the matrix that I'm looking at is negative 1, positive negative 1, 2. Why so big? So I have a 1, a negative 1, and a 2. I have a 0, a k, and a 1, and a k, and a 1, and a 3. Now you'll notice in the book they'll start writing this. They're supposed to write this, but they stopped doing that. And the reason for that, there's nothing you could do for those because anything you multiply to change them, whatever you multiply 0 with is 0. Add it to a 0, that's always 0. So they start doing the problems from now on without this. They just start doing it this way and reduce it any way they want and play with it any way they want. So if they take negative k row 1 plus row 3 and row 3, what would happen? Of course, if there's a line, that will be 0 still. And negative 1 times k is negative k plus k is 0. Negative 1 times negative k is positive k, 1 plus k. And negative k times 2 is negative 2k, and this will be 3 minus 3. What did I say it was? I lost track. K1, 3 minus 2k. Okay, and the next, again, you could say 0, 0, 0, that doesn't matter. The next step, I'm gonna take the opposite. So negative k minus 1 multiplied by row, no. Let me just double check. Okay, I found a mistake. I knew there was something wrong. That should have been a 1. 1, 0, 1k. So that should have been a 1. But when I worked it out, it didn't work out this way. And if I take negative row 1 plus row 2 and row 2. So negative plus, that's a 0. 1 plus k. And negative 2 plus 1 is negative 1. Okay, so if I take negative row 2 plus row 3, put the result in row 3. Negative, negative, that's a 0. And 1, that's 4 minus 2k. And as you see here, well, instead of solving this is a triangular matrix, I could just say the determinant of this. That's a quick way. Determinant will be 1 times 1 plus k times 4 minus 2k. Now, very easy. If the determinant equals 0, this will have no solution. If the determinant equals 0, you'll have no solution. And if it doesn't equal to 0, so if k doesn't equal to -1 or 2, well, let me put it this way. If k equal 1 or 2, we'll have linearly dependent, and any other value. So if k belongs to any real number, except -2 and 2, the system will be linearly independent. So it's linearly independent for any value of k other than -1 and r2, because that will force the determinant not to be 0, and therefore there's a solution. And here it says, by using appropriate identity where required, determine which of the following are linearly dependent. Well, we know sine squared plus cosine squared equal 1, so we know if you multiply -1 times 6 plus 2 times this plus 3 times that, that is -6 plus 3 times this. I'm so stuck on theta. Old habits are hard to die. 6 sine squared of theta plus 6 cosine squared of x, not theta. That would be -6 plus 6 into sine squared of x plus cosine squared of x, and we know that that's a 1. So that is 0. So this is linearly dependent because these two are multiple. These three are multiple of each other. I could multiply those two by numbers and get the third. Similarly here, I'm not sure how comfortable you are with this, but we know that cosine of 2x has 3 identities. One of them is the cosine squared of x minus sine squared of x. So simply, if I take cosine of 2x minus, plus sine squared of x minus cosine squared of x, so multiply this by a -1, this by a +1, you should get that. If I get a 0, then that will be the cosine squared of x minus sine squared of x plus sine squared of x minus cosine squared of x, and that will be 0, which means these are multiples of each other, therefore they're linearly dependent. How about if I have two functions? One is sine, the other is cosine. It says the functions are linearly independent because neither is a scalar of the other. Confirm this using Wronskian. Wronskian, well, basically the way it works, you list the first function, you list the second function, you take a derivative, and the determinant of those will be the product of those minus the product of those, which would be negative sine squared of x plus cosine squared of x, which will be -1 and not equal to 0. Therefore, it's linearly independent. That simple. Well, this is the basic problem. If I look at the next problem, this one is a bit more work. Find the Wronskian. E to the x e to the x, and x squared e to the x. Now, I could do a few things on this problem. I'll do it after I get the actual values. Well, this is e to the x, this is e to the x, this is derivative of the first times the second, plus x times e to the x, derivative of the first times the second plus x squared e to the x. And this derivative will be e to the x plus derivative of this is 1 times e to the x, that's e to the x plus x e to the x. Here, the product rule, 2 times e to the x plus 2x e to the x. And derivative of this would be plus 2x e to the x plus x squared e to the x. So if I take e to the x out of this whole mess, nope, not 3, I messed up. That would be 2 plus 4x plus x squared. Let me just double check my work really quick before I go on. Okay, I could take negative rho 1 plus rho 2 and rho 2. And negative here. Rho 1 plus rho 3 and rho 3. I'm trying to make it a triangular matrix. Negative x, that's a 1. X squared, that's a 2x. And negative, that's a 0. That's a 2. And that's a 2 plus 4x. So far, so good. And I could also take negative twice rho 1 plus rho 2 and rho 2. Remember, that doesn't alter the work in any way. Multiplying this by a negative 2 plus, that's a 0. And that's negative 2x, that's 2 plus 2x. Found it. When we did this, negative 1 plus 1 is 0. Negative x, that's 2. That works well. Now, I thought it did. Yeah, that was right. When you multiply this by negative 2, negative 4x plus 4x, that disappears. We're left with a 2. There we go. And now I could say if I could put this row and column, that is e to the x times 2, which is 2e to the x, and that would never equal 0. And our conclusion is that, therefore, this is linearly independent set. There's the homework, and that pretty much concludes this section.